So this is our fourth computer session. This will be a long one, but a very important one. We're actually going to write the MATLAB code which generates a two-dimensional spatially variant lattice. In following sessions, we'll do 3D spatially variant lattices. The assumption is that you've listened through all of the theory slides and also followed the first 3 computer sessions. That will let us move a little bit quicker through some of the sections of code that we described in more detail in previous sessions. With that said, we're still going to type every line of code here and talk about it. We just may skip some details that we've covered in a prior session. So as usual, the first thing I like to do is initialize MATLAB. I close all the figure windows, clear the command window, and the most important, I clear memory. Now I'm going to define a unit, and the only one we'll need here is degrees. I define that as pi over 180. This lets me create variables such as theta equals 45 times degrees. I think it makes the code a little bit easier to read and to follow, and it helps me think through the code. Now we're going to open a figure window, and what I like to do is make the background color white, and that lets me copy graphics and paste it into publications or presentations. Now, since I do not know how big your monitor is, and it's probably bigger than the one I'm using here, we're going to use normalized units for when we define the outer position of the window. So this code will open up a figure window that has a white background that is full screen regardless of how big your monitor actually is. Now we're ready to start. Right up front in my codes, I include what I call the dashboard. This is all of the hard-coded numbers, how many points on your grids, sizes of unit cells, permittivity values, all these types of things. I don't perform any work or calculations in the dashboard. Then after the dashboard, when the code starts, no hard-coded numbers, just calculations, and everything's done relative to the dashboard. That lets us control everything about our code through the dashboard. Well, we need to define one thing in this case about our unit cell, and that is the size. So we will say that this lattice has a lattice spacing of 1. We don't need to define anything else because later on we're going to build a picture of the unit cell in a way that makes it a grayscale unit cell, and that'll make more sense when we get there. But this is all we need right now. We'll need some grid parameters. In this code, we're actually going to have 3 separate grids. One grid we'll build just a single unit cell on, and we'll use that to do what we'll call a fill fraction sweep. We need to know the relation between our threshold and the fill fraction. And since our unit cell probably doesn't have exactly a cosine profile, that technique of cosine pi times f may not work. So we'll do this a little bit more rigorously and accurately. So we need the grid for the unit cell. So I'll call it NXH, and we'll make that 255 points. Call that unit cell grid, and an NYH, also 255. Now we need to start talking about the lattice, the overall two-dimensional lattice, and we'll make this 10 periods by 10 periods. Then we will define 2 parameters that help us choose the resolution of the grid. So we'll have 2 grids that we'll be building our spatially variant lattice on. There's NRes low, we'll set that to 10, and NRes high, and maybe we'll set that to 20. So NRes low will be number of points per period. And so will NRes high. The difference is, if you recall from the theory slides, that the function or the data in the grating phase is very smooth and slowly varying. We can draw those types of pictures and represent that data with a very coarse grid, a low resolution grid. But then if you'll recall, our gradings can be very fast and very, very abruptly, and we need a rather high resolution grid to resolve those. So it doesn't make sense to do all of the work up to and including the calculation of grading phase on a super high resolution grid if we don't need it. So what we'll do is we'll do all that work on a low resolution grid, and once we calculate this grading phase, all we'll do is interpolate it up to a high resolution grid and then calculate our lattice. So it'll make more sense when we get there, but that's what NRes low and NRes high is. So we have three grids: the unit cell, and then we have a low resolution for the lattice and the high resolution for the lattice. We also want to define our Fourier expansion parameters. So we're going to FFT our data, that's our Fourier expansion, and grab a window. And for right now, we'll grab a window that's 7 by 7 Fourier coefficients. We're going to come back later and do something a little bit different here that makes things a lot more efficient. But for now, we'll stick with a 7 by 7 window of our Fourier expansion. Okay, next section of the code, we'll calculate our grids, the low resolution and the high resolution grids. So the first step is the low resolution grid parameters. We'll start off with dx being our unit cell width divided by NRes low, because that's how we defined NRes low, number of points per period. Do the same thing for dy. Now we're in a good position to calculate how many cells there are in the grid. We'll round up, but it's the physical width divided by the cell spacing, and we round up, and now our grid could be slightly different than the physical width we defined up above. So what we'll do is we'll recalculate dx, make it a little bit smaller so that dx, sx, and nx are consistent. And we'll do the same thing for ny now. Now that we have the number of points and the cell size, we can create our axis vectors. So we'll create one for the x-axis. Remember, this is an array telling us the position of each point as we move horizontally across our grid. And YA will be the point, the position of the points moving vertically. And then the last step, let's make a mesh grid out of that. So that's our low resolution grid and everything about it. Now we have our high resolution grid. We want to represent the same physical amount of space, just with more points. Now it's a little bit more complicated to determine the resolution of this high resolution grid. Remember, we have an expansion. We have decomposed our unit cell, or we will decompose our unit cell, into a bunch of planar gratings. We have to figure out which of those planar gratings has the shortest period. And the one that has the shortest period actually has the highest grading vector. So first, let's figure out what is the maximum grading vector that our code could possibly see. Well, it's 2 times pi over the period times the maximum indices from that little window that we'll grab. Let's run this for 2 reasons. Make sure we don't have any errors, and we can also look at what Kmax is. Okay, we'll close that graphics window. No errors, that's good. Kmax. So that is the maximum possible grading vector. And we see 2 numbers. It's the x component and the y component. There's no z component because we're in 2 dimensions. From that, we can calculate the minimum period, which is just 2 pi over the magnitude of Kmax, and we can use the built-in MATLAB command norm to do that. So norm Kmax will give us the magnitude of the Kmax vector. And if we highlight the line and hit F9, it'll run just that line, and we can see what A min is. So notice we're talking about a lattice with lattice spacing of 1, But in this case, we chose a 7x7 grid of planar gradings, and it turns out the one that has the shortest period has a period of about 0.2357. So it varies much more rapidly than the lattice itself, which is why we had to do this. Now we can calculate the resolution on this high resolution grid, and we'll name it dx2 so we don't overwrite our low res grid, which is just dx. So dx2 is this A min divided by n res high. And do the same thing for dy. Now we have our resolution, and next what we want to do is figure out how many points should be on this grid. And now that we know our grid resolution, we also want to cover the same physical amount of space that the low resolution grid does. So since it's the same physical amount of space, we still just use Sx divided by the resolution of the high resolution grid, and that'll tell us how many cells. We do the same thing for y. And now we know how many points should be on this high resolution grid. Now there's a variety of things we can do here, but we're going to calculate these axis vectors for a high resolution grid. But to make the interpolations a little bit easier, we're going to start and stop these axis vectors on the same exact point that the low resolution axis vectors start and stop. We can do that real easily with the linspace command, and we'll tell it to start at the first point in XA. We'll tell it to end at the last point in XA, but we want this done with nx2 number of points. We'll do the same thing for ya2. We'll start at the first point in the low resolution grid. We'll end at the last point in the low resolution grid, but we'll do it with ny2 number of points. Now that we've used linspace, it turns out the spacing between our points is not exactly dx2 and dy2. So we will recalculate those. dx2 is x, the second point in xa2, minus the first point in xa2. We'll do the same thing for y. Now we have correct values for dx2 and dy2. And the last thing, we'll mesh grid these. And we've calculated both of our grids for doing a lattice. We said we had 3 grids going on here, but the grid for the unit cell only is ever used when we're doing this fill fraction sweep and building the unit cell. So that's what's next, and we'll calculate that grid in that section of code. So I'm just going to scroll up, copy that section header. I like to copy and paste rather than retype each time. What we want to do now is build a grayscale unit cell. So now we need our grid, unit cell grid, and hopefully by now you're getting the pattern of how we do this. So the resolution on this super duper high resolution grid is A over NXH, and NXH is the number of points on this grid, and we've already defined that up in our dashboard. TYH is A over NYH. Remember, A is the lattice spacing. You divide the lattice spacing by the number of points, it gives you the cell size. We need our axis vectors. And I guess because I'm strange, it also, when we do things with mesh grid, it helps me think a little bit if I center our axes about 0. So all we have to do is subtract the mean, and we can do that. And then the last thing is to generate our mesh grid. Now we have our grid calculated, number of points, cell size, axis vectors, and mesh grid. We're ready to do a lot of work. We want to make a triangle, but we're going to make a grayscale unit cell, which is something different that we haven't done yet. So what I like to do first is to define the vertices of the triangle. We'll calculate the height of a triangle. We're calculating the height of an equilateral triangle where each side has length W. And let's define W as, I don't know, 0.9 times A. Since we're doing a grayscale unit cell, it won't actually have a width. But what we need to do is figure out just any 3 vertices for any triangle, and this will all work just fine. So 0.9a, and then we'll say h equals w times square root of 3 over 2. That'll be the height of that equilateral triangle. And now we can calculate our 3 vertices. So if we put the point at the top and 2 points down at the bottom, the point at the top will be 0 over and h over 2 in the vertical direction. Next vertice will be at minus w over 2 at minus h over 2, because we're talking about the bottom of the triangle. And V3 will be at positive w over 2. I know we don't need the plus sign there, but I kind of like it because it goes with a negative sign, and I guess I see what's going on a little bit easier in my mind. So that defines the 3 vertices of the triangle. Now we want to make a grayscale unit cell, so we can't just fill in zeros and ones. We're going to do something a little bit different. And let's pop open Google real quick, and let's search for distance from a point to a line. And if we go to Wikipedia, it provides us some equations about how to calculate the distance from any point to any line. So in this case, we're using this equation I have right in the middle of the screen. So we have points x1, y1, that's the first point, and x2, y2 is the second point. We have a line connecting that. And then we have a third point somewhere, x0, y0, and we want to know the distance from that point to the line. And so this is the equation that we're going to use. Okay, back to MATLAB. Section 1, and what we're doing will make sense after we plot it. We'll plot it and show you what's happening. So I'm going to pick 2 points that'll define either side of the line. So we'll pick vertex 1 and vertex 2. Now I want to calculate the distance of every point on our grid to that line, and I'm using that equation that I showed you on Wikipedia. So here's implementing that equation. 2, 2, 2, P12 times XH, P21 minus P11 times YH, that's the numerator. Sorry, D1. Okay, unless I've mistyped, that is the equation on Wikipedia. Let's plot this just to make sure we have it right. So we'll say image SC, say YA. We'll do a P color actually. Color, axis equal tight, and a color bar. All right, we'll run it, make sure there's no errors, and we can also see what D1 is. And we have an error somewhere. What did we do? Okay, it looks like we're missing a parenthesis. Try again. Still have an error. Oh, I'm sorry. Yeah, so D1, we're on our unit cell grid, which we had XAH and YAH. So I was using the wrong XA and YA. Okay. So we have a value of 0, that is this light colored blue, which is somewhere right around here, which makes sense. That would be that upper left side of the triangle. And notice one other thing. Notice the numbers go negative to one side and positive to the other. And that was actually something a little bit different I did than the equation. If we go back to that equation, notice there's this absolute value or magnitude symbol outside of this. I didn't include that in my equation. If I did, it would be positive numbers on both sides, but in this case I don't want that. I want it to go negative on one side and positive on the other, so I can differentiate what's inside and what's outside of the triangle. And by the way, we could get this to look a little bit better if we said shading interp. Let's run that again and see what happens. Okay, same thing. The zero's on the light blue, so we're talking about this side of the triangle. We picked vertex 1 and vertex 2, so it makes sense that this is what we would get. Okay. I'm going to add a semicolon here so we don't keep seeing V1 at the command prompt. I wrote it this way, copying P1 and P2 over so that we can just copy this entire section of code. Call this section 2. And we'll use vertex 1 and vertex 3, but now we're calculating distance 2. And we'll have a positive sign here, and you'll see why in just 1 minute. Let's go ahead and plot this. So now we'll be looking at D2, assuming I haven't made any typos. Here we go. Okay, D2. 0 is still in the light blue. Now we're going down that upper right side. And the reason I flopped the sign is because otherwise we would have negative numbers down here. And what we want are the positive numbers. We want this function grading towards positive toward the inside of the triangle, away from the line. Section 3. This will be the bottom line, and we'll use vertex 2 and 3. We'll call this distance function D3. Whoops. And we'll go back to a negative sign, and let's go ahead and look at what D3 is. Now 0 is a darker blue, so this is actually the 0 here. And it's going positive in the upward direction, which is why we included the negative sign. Now from here, we want to combine all three of these. So here's where we actually build the unit cell, a grayscale unit cell. So UC for unit cell, we'll take the minimum value of D1, D2, and D3. Now min doesn't like us to have 3 input arguments, so we'll just say UC, comma D3. That'll take the minimum value from all 3 of those. Let's go ahead and look at what that would look like. A little bit lopsided, isn't it? Let's proceed. Let's subtract the minimum value and divide by the maximum value. This puts unit cell in the range of 0 to 1. Let's run it again. And we see our triangle, but still a little bit lopsided. Let's try to figure out why it's lopsided. These all look good. 1, 2, 1, 3, 2, 3. 2. Okay, I think I figured out our problem. We need to move that squared outside of the parenthesis. Alright, sorry about that mistake. Let's run it and see if we get a nice symmetric triangle. Okay, there's our nice triangle. And we can see now we can set a threshold and control whatever size triangle we want. Okay, very good. So we're showing our unit cell. Let's do this a little bit more sophisticated. Show unit cell. We're going to show a bunch of different things, so let's subplot this to 2, 3, 1. And as I mentioned before, I really usually like to use image SC. It gives me, I think, a more intimate connection to the data because I can actually see the pixels, the data when I zoom in. But image SC draws things upside down. So what we want to do is get a parent to that handle and then set YDIR to normal. And for image SC, that defaults to reversed. Got an axis equal tight. We don't need the shading interp anymore because that was for P color. And we'll give it a title. Okay, let's run it, make sure it draws it in the right position. And of course we have an error. We used HH for the handle, but only put H there. I'm using HH so I don't overwrite the height of the triangle, just in case we want that later. I don't think we will, but we don't want that later. Okay, so there is our unit cell. And we're done that section of code. The next section is to figure out what threshold value corresponds to what fill fraction. So we need to do a fill fraction sweep. I will copy and paste our section divider so I don't have to retype that. Perform fill fraction sweep. Now, just thinking about this intuitively, we think, okay, we want to realize a certain fill fraction. What threshold is necessary? And for grayscale unit cells, it's not exactly straightforward. So what we'll do is look at this the other way around. We'll start with the threshold, build the unit cell, and figure out what fill fraction we got. We can then fit that to a curve, and then later on, when there's a certain fill fraction we want to realize, we can use that curve and interpolate what threshold value is needed to realize that fill fraction. So here, when we're doing the sweep, we will start off with the threshold. So GTH for our threshold, underscore data, meaning this is the data curve for it. And we can take it from 0 to 1. We've scaled our grayscale unit cell to go from 0 to 1, so it makes sense our threshold will go from 0 to 1. And let's do 100 points. Next section of code, we will calculate fill fraction data. So first thing we'll do is we'll initialize the fill fraction data. And I like to do something like this, 0 times GTH dat. That way, no matter what length GTH dat is, FF dat will be the same length. Now we set up a for loop for n equals 1 to length of GTH dat. So this loop will essentially be going from 1 to 100. First step is to calculate the binary unit cell. We have the grayscale unit cell above, so we construct the binary unit cell using the threshold technique. So we'll call that UCB for unit cell binary. Is our grayscale unit cell greater than or less than, we can do it either way, GTH dat n. So this gives us a single number threshold, and we will get some kind of binary unit cell. Given that, we want to figure out what fill fraction that binary unit cell is. So FF dat n, and here's where we calculate the fill fraction. So the binary unit cell is all zeros and ones. We want to know what fraction of those cells contain ones. So all we have to do is sum UCB and then divide by the total number of points. And that'll give us our fill fraction. Now to get a better idea of what's going on, let's illustrate and plot what is actually happening here. So we will subplot to, let's see, we did 2, 3, 1 up here. So we'll go to 2, 3, 2 here. We'll show the binary unit cell. And I will copy and paste the code here, so I don't have to retype that. And if I highlight this and hit Control right square bracket, oh, I missed one, it'll indent everything for me. So I'm drawing UCB, and I'll name this the binary unit cell. We also want to see our fill fraction sweep. So we'll subplot that to 2, 3, 3. And we will plot GTH dat 1 to n, so we're only displaying the numbers that we've calculated up to this point. And to make this look a little bit better, we'll set our x-axis limits. Because if we're only plotting 1 to n, it'll scale to only show 1 to n. I want it to scale the whole way over, and we can watch the line form the whole way. So GTH dat first one, and then max GTH dat for the last one. And we'll do the same thing for the y-axis limits. And again, this is so the limits don't move around. That has to be limited between 0 and 1. And in this case, the x-axis is the threshold value, and the y-axis is our fill fraction. And if we want to see this happen in real time, we need to put a draw now in here. It's probably going to run real fast, so just that we can see it, let's pause a quarter second between each iteration. So now we're going to run this, and hopefully we haven't made any mistakes. I think we've paused a little too much, but that's not too bad. What we can see as the threshold value is increasing, we're getting a smaller and smaller triangle. Right now it's still off of the screen, but eventually the triangle will get smaller and smaller. And at this point our triangle is fully contained, and it keeps going. Now we have a nice curve. If we want to realize some fill fraction, we can use that curve to figure out what threshold value did that for us. Okay, so we'll close that. Now, I'm not interested in seeing those graphics every time. There's a number of things we could do. What I'm going to do is just delete this graphic here. Just not do it inside the loop. We'll move this stuff to outside the loop. And it runs very, very fast. We'll run it and you'll see. So we don't need the pause anymore. And we'll plot this to 2, 3, 2. We do not need to go 1 to n anymore because it'll be entirely calculated out here. So show fill fraction sweep. Okay, so watch how fast this is when we run it. It ran that fast. So we see our grayscale unit cell and our fill fraction sweep, which relates fill fraction to the threshold value. And we don't need the draw now. Okay, we are on to the next section of code. This is where we take our unit cell and do a Fourier expansion. So this should be pretty straightforward if you've looked or watched session 3. Compute Fourier expansion. First step is to calculate the FFT, the two-dimensional FFT, and we'll store all the Fourier coefficients in A. So we'll start off by saying FFT2. That's a two-dimensional Fourier transform of our grayscale unit cell. Now, if you remember, the FFT2 throws all of the business off into the corners. We would rather have this centered. So we'll follow that with an FFT shift. You'll also recall that the scaling was off. We have to divide by the number of points. And our unit cell was on a grid of size nxh and nyh. Now what we want to do is truncate that Fourier transform, just like we did in computer session 3. And pull off this little window. Right now we have it defined as 7 by 7 Fourier coefficients. So what I like to do first is calculate the array indices inside A that corresponds to the zero order Fourier coefficient, or the DC value. And we calculate that simply as nxh over 2 and q0 and yh over 2. Okay, so those will be the array indices in A to the zero order Fourier coefficient. Now we want to calculate the start and stop indices of our window. So we'll start going left to right at np1. So that's simply p0 minus floor of np over 2. The stop, or the right-hand side of our window, is basically the same thing but with a positive sign. And we'll do the same thing for the vertical direction. Instead of p, we're calling this q. So we have a q naught instead of a p naught, and an nq instead of an np. Now we have the array indices in A of the little 7 by 7 array, or np by nq array of Fourier coefficients that we want to extract. So let's extract that to AT, and that is simply A from np1 to np2 and q1 to nq2. A is our truncated Fourier series. So let's show that to the screen. Let's plot that with image SC. So I'm going to borrow this code. I guess I shouldn't say I'm borrowing it because I'm not going to give it back. But I'm going to change it. Show truncated FFT2. We will subplot this to 2, 3, 3. And we're going to image SC AT. Now these are complex numbers, so we either have to choose to show the real part, the imaginary part, or the absolute value, or something like that. I'll just choose the real part. I just want to see that there's numbers there and they look like they're making sense. So we'll label that FFT2. And we guess we can call it the truncated FFT2. So let's run it and see what we get. Make sure we don't have any errors. Okay. Our grayscale unit cell, our threshold sweep, and our truncated FFT. You may notice that it looks like our Fourier coefficients are a little bit more confined to the center, and that's actually because we've smoothed our unit cell. If you've seen the same thing generated for a hard triangle, there's higher order Fourier coefficients. In DSP, they call this windowing theory. I'm not going to get into it now, but when you have a grayscale unit cell, you can expect your Fourier coefficients to be, I guess, better confined to the zero order component. So remember, there's two parts to a Fourier expansion. We have to calculate the amplitudes of our plane waves in the expansion, and that is the FFT. So A, or AT, contains those amplitudes of the plane waves. And then analytically, we calculate the grading vectors associated with each one. So first, I want to calculate the indices of the Fourier axes. So this is the equivalent of XA and YA, but on our Fourier space grid. So we have a PA and a QA. And we're going to go from minus floor NP over 2 to positive floor NP over 2. And I'll copy and paste this to do a QA. And next we'll calculate our grading vector expansion. So Kx is 2 times pi times that array of integers PA over the lattice spacing A. Ky is pretty much the same thing, but it's using the integer array QA. divided by A. And then we'll mesh grid those because we have a mesh grid of grading vectors. And that's it. So we've done our Fourier expansion. We've calculated the amplitudes of the planar gratings. That is now stored in AT. And we've calculated our expansion of grading vectors. Each one of those Fourier coefficients has its own grading vector that we're storing in Kx and Ky. Next section of code. Okay, in this section of code, we're generating our input data. So these will be the maps or the pictures of how we want to spatially vary the period, how we want to spatially vary the orientation, and how we want to spatially vary the fill fraction. So we'll rename this section to generate input data. And the first section here, period. And just to remind us, we're building this on a low resolution grid. Remember, we're doing all of the work up to and including calculate the grading phase. Then we interpolate to a high resolution grid, then calculate the planar gradings. So the period is built on a low resolution grid. And maybe I didn't have much of an imagination, so I'm not going to do anything with period. We're just going to keep it at A everywhere. Orientation of the lattice, also done on the low resolution grid. And let's do an arcing pattern. And then fill factor. Now the fill factor, remember we put this in at the very last step, and we're doing this on a lattice, and the lattices are generated on the high resolution grid. And I guess I was a little bit more imaginative here. So I'm taking the mesh grid x2 parameter minus sx over 2, and you'll see what this is doing. We're going to make a little bloat of the fill fraction in the middle of our lattice. But right now we have the origin of our grid off to the lower left. So I'm subtracting sx over 2 and sy over 2 so that the origin of this function right now is at the center of the grid. So let's go ahead and look at what this looks like. So let's clear the figure. And we'll do a p color xa2 ya2 ff axis equal tight. And what we'll see, unless we made a mistake, it's a bloat looking thing. We need a shading interp. Sorry about that. Okay, so we have this little circle bloat thing, and what we'll do is we'll scale that so that we have the fill fraction varying between two different values. So we got our nice circular bloat. And before I scale it to two different fill fractions, I like to make the fill fraction go exactly between 0 and 1. So we'll subtract the min and divide by the max. And we'll invert it. And then last, we'll do the fill fraction 0.05 plus 0.3 times FF. And let's just go ahead and look at what that is. Let's give it a color bar so we can realize what we're doing. So what we see is we'll have a low fill fraction on the outside, and we'll come into a maximum fill fraction of 0.35 in the middle. So that's what's happening. So the last thing in this section of code that I like to do is display everything. So let's show input data. And we'll erase this. I'm going to borrow the image SC code from up here. And we'll subplot to 2, 3, 4 now. And we'll show the period. We don't need the real operation because period is always real. That'll show period. We have our theta. We'll subplot that to 2, 3, 5. And let's divide by degrees, so it's a little easier for us to interpret. And then the last thing, we'll subplot to 2, 3, 6, and we'll show the fill fraction. Okay, let's run this and make sure we got everything right. Okay, so that is everything we need. We have in the upper left, we have our grayscale unit cell. We have our threshold versus fill fraction sweep. Then we did our Fourier expansion. And all I'm showing here are the amplitudes, but we've also calculated the grading vectors. And then how do we want to spatially vary the lattice? Everything's down here. We'll keep the period constant. The orientation will change, so we're going to make some sort of rainbow of the lattice, some kind of 90-degree bend, if you will. And we'll bloat the fill fraction according to this map. We'll do a draw now because we'll want to see that while the rest is calculating. So that is it for that section of code. On to the next one, and this is the main one where we actually generate the spatially variant lattice. So let's go ahead and copy the section divider, and we'll name this generate spatially variant lattice. The first thing we're going to do will look a little bit weird, not too big of a deal, but this is going to let us do something to improve efficiency later, and I'll talk about that when we get to it. So generate list of planar gradings. Right now, we have the grading vector expansion and the amplitudes of our planar grading stored in two-dimensional arrays. What I want to do is stretch them out into a single linear array. So we'll have a list, if you will, of grading vectors. So let's go ahead and run this. We'll go to the command prompt and I'll show you what klist is. Klist, it's the list of our grading vectors. So this first one here is our first grading vector, second grading vector, third grading vector, and it just goes on and on and on and on. Might make a little bit more sense if I displayed it transposed, and now you can see our entire list of grading vectors. And we'll stretch out our list of the amplitudes as well. So we created a serial list of all of our planar gradings, and we don't have to keep the order. We could randomize the order, and in the end we would still build our lattice just fine. Okay, finally our main loop for generating this lattice. So we will iterate over our Fourier expansion. First thing I like to do is figure out how many planar gradings we have. And it's the length of C list. And we will initialize our spatially variant lattice with all zeros. And the lattice now will be on the high resolution grid, so we're using NX2 and NY2. And then our loop. We will loop over all of our grading vectors. And that's our main loop. So now what we've done, we've taken our unit cell, expanded it into some set of planar gradings, and then we're spatially varying each planar grading independently and adding up all of those spatially variant planar gradings. And we have a four-step process for spatially varying a planar grading. Step 1 is build a K function. Step 2 is to solve for the grading phase. Step 3 is to calculate the analog lattice, and step 4 is to calculate the binary lattice. So our first step is to calculate the K function. So what I'll do is I'll pull off the Kx and Ky components from klist of our grading vector. So that should be pretty straightforward. So now Kx and Ky are both single numbers, and it's our current grading vector. So rather than express that grading vector in terms of x and y, I'm going to calculate its angle and magnitude. So theta and r, after this calculation, will still be single numbers of the angle and magnitude of our grading vector. Now we're going to convert back from polar coordinates to Cartesian coordinates. And if I just said theta r, we would get back the same exact grading vector we started with. But instead, I'm going to add our 2D function theta to that. And to r, I will multiply by a and divide by our period. Oops. A. And what this will do is it'll make kx and ky two-dimensional arrays where it's essentially the theta and PER arrays, but we've added theta to our two-dimensional theta array, and we've rescaled the magnitude to be consistent with period. So at the end of this, we have our k function. Now we want to solve for grading phase. And we'll use the code that we provided on the website. And phi equals SVL solve. We'll give it kx, ky, and the grid resolution parameters dx and dy. At this point, we'll have the grading phase. So all this work has been done on a low resolution grid. Now we want to take that grading phase to the high resolution grid before we calculate the planar grading. So we'll interpolate high resolution grid. We'll still use phi. We could use a phi 2 or something like that, but since we don't need the original phi, we'll just overwrite it. We'll use the interp2 command to do that. Now we have our grading phase on this high resolution grid. If we plotted both of those, they would look the same to us. We wouldn't be able to distinguish them. It's just that one of them has more points than the other. Now we're ready to calculate the analog planar grading. The analog planar grading that corresponds to whichever planar grading we're in the process of calculating in our loop here. We'll call it GA. And it's a complex exponential, 1i times phi. And that's it. We have our planar grading. And then we add the planar grading to our overall lattice. And this is also where I like to incorporate the Fourier coefficient. We could have just as easily taken the C list, the amplitude, and put it up here. Either way works. For whatever reason, I'm starting to prefer this ordering. So that's it. We're actually done. The generating of the grayscale spatially variant lattice. What we want to do is add some graphics to this to visualize what's going on. So let's refresh the graphics. CLF. We don't need to know and see our input arguments anymore. We're going to erase those, clear the figure window, and we'll just display two things. On the left, we will show our current planar spatially variant grading, and on the right, we'll show the overall lattice. So we can see each of our planar gratings individually, and we can see the overall lattice get better and better and better, or form into the final lattice as we add the planar gratings to it. All right, so show planar grading. We'll borrow our image SC code again from last time so we don't have to retype it. And I hit the control right square bracket that indents it. And we're just displaying two things here, so we'll subplot to 1, 2, 1. And what we want to display is GA, our analog grading. However, that is a complex number, so we'll just show the real part of it. We'll label this our planar grading. I'll copy and paste that. And the last thing we want to do is show the overall lattice. And that is SVL. And the magnitude of the imaginary component of this will sort of come and go as we're adding different Fourier coefficients. So in general, it will have an imaginary part. So we'll just display the real part of it. And we'll call this the analog lattice. And then the last thing, we want to force MATLAB to update the graphics. To draw graphics. That's just a draw now. Okay, I don't know how fast this will be. If it's too fast, we'll slow it down with a pause, but we'll go ahead and run it. We'll look for any errors and fix them if we have any errors. So let's go ahead. Yeah, I think we have an error. Oh, I just typed G. It needs to be GA. There we go. We did not do our subplots correctly. Should be 1, 2, 2. So on the left, we're looking at our planar gratings. And on the right, we're looking at the overall analog lattice as we're adding each of those planar gratings. And what we'll see is it slowly and slowly improves until we have a spatially variant lattice with our grayscale unit cells spatially varied across it. Okay. Now here's one trick. We used our graphics. We could see that everything's working. It helps us understand what's happening. But I probably don't want to display those graphics each time. So one quick dirty thing we can do, we can say if 0, then after the draw now end, and just for clarity we'll indent what's inside that if statement. So if 0, that 0 will never be 1. It won't run the graphics. So we've just turned off the graphics in a quick, simple way. And now if we run it, it'll run very fast. And we'll come away with our lattice. One of the last things we want to do is just clean up any numerical noise. In an ideal world, the SVL array that comes out of this, our spatially variant lattice, shouldn't have any imaginary components because we took a symmetric unit cell, we Fourier transformed it, we have symmetry with our Fourier coefficients, etc., etc. So there shouldn't, but there will be a small imaginary part. So I just like to clean it up with real SVL. So we now have a purely real valued SVL. Then our original unit cell was scaled between 0 and 1, but since we've truncated the Fourier coefficients, that scaling may not be exact. So we could choose to divide by the minimum and then subtract the maximum, or subtract the minimum, divide by the maximum, sorry. There are times where it's actually best not to do this, but I don't know. Leads to slightly cleaner data, I think. Okay, now we have our cleaned up spatially variant lattice. We want to generate a binary lattice from this. So let's do that. Generate binary lattice. This is where we'll consider that fill fraction sweep that we had done previously. So first, we need a two-dimensional function, which is our threshold value everywhere. So how do we get that? We have, or right now we know, the fill fraction everywhere, but we have to convert this to that threshold number to realize the fill fraction. And we will use interp 1 to do that. So we're essentially doing an interpolation on this curve, now treating fill fraction as the x-axis and the threshold as the y-axis. And we say interpolate that for all of these different fill fractions we're interested in. And notice we've stretched this out to a 1D array. That's because we're using interp 1. And then we come out with a 1D array. So we'll reshape that GTH back to a 2D array. Now remember, this is on the high resolution grid, so we'll use NX2 and NY2. And now we can create our spatially variant lattice that's binary as SVL greater than GTH. And if we use SVL less than GTH, it's the same lattice, just inverted. So whichever you prefer, and we can switch that back and forth depending on what you're doing. So we've essentially generated the lattice. We're done. Let's show them. So show final lattice. Go to the command window. I want to go borrow the graphics from up here. And we don't need the real anymore because we've already done that. SVLB apostrophe. So we're showing our binary lattice. We will give it a title consistent with that. Binary spatially variant lattice. So this should run much quicker because we've turned off the graphics inside the main loop, and unless we've made a typo somewhere, this should run and give us a binary lattice in the end. And there's our binary lattice. Notice the fill fraction is a little bit higher in the middle than it is on the outside. That's one of the things we did on purpose. We didn't choose to spatially vary the period at all, but we certainly could have. Now notice how long that took. Let's think of a more clever way to speed it up. What we could do is, rather than truncate our Fourier coefficients by windowing the Fourier transform, we can create a huge window, incorporate a bunch, and look at the magnitudes of the Fourier coefficients. If the Fourier coefficient is really small, that planar grading really isn't significant, and we could drop it, in fact. So let's go back up to our dashboard, and under Fourier expansion parameters, we'll come up with a threshold for our Fourier coefficients. We'll say something like 0.01. And what this means is all Fourier coefficients that are 0.01 times the maximum Fourier coefficient or larger, we will retain. Anything smaller than that, we will drop. So now we're going to go back down to right after we created the list of our grading vectors and Fourier coefficients. And the reason we made that list is so we could do this new truncation real easily. So let's say truncate list. First, we want to figure out what is the biggest Fourier coefficient. So we look at the absolute value of everything in the C list and pull off the biggest one. Now we want to grab the array indices in C list of all the coefficients that are bigger or equal to than 0.01 times C max. So again, we'll look at the magnitude of all the Fourier coefficients, and any of them that are greater than CTH times C max will come out and give us an array index of all of those. So ind is an array index of all the ones that we want to retain. So we'll just say C list is C list ind, and now we have this list of only the ones that are big enough to incorporate in our expansion. And we also want to do the same thing for K list. And that's it. We now have a code that'll run much faster with very little hit in the quality of the lattice. Let's go ahead and run it and see what happens. You might notice that ran a lot faster, or a bit faster, but it's not looking that much better. And that's because we still have our window set to something relatively small. What we could do now is set this to something like 51 by 51. This will take a little while, but we're going to get a really good lattice. Let's even set this to 0.05. We could have never done this. We could have never done this many without waiting all day, without using this threshold technique. Now, certainly if you want to let your computer run for a couple days, we could do that. But we can do it in just a minute or so here. So we'll run it. And we should generate a lattice that looks really nice. guess I'll point out while we have time, this lattice is only 10 by 10 unit cells, and we have a feeling of how long things are taking here. This gets worse in 3 dimensions, and as we progress, we'll incorporate more and more tricks that will help us get away with coarser grids to make things run faster. So this way of truncating by the amplitude of the Fourier series coefficients is a very good technique. There are more, it's just beyond the scope of this short course. There's another class I teach, 21st century electromagnetics, where we teach those in detail. Maybe I was a little ambitious in terms of the number of terms we're retaining here. I guess I like really good lattices. So this code is essentially done. We only have one more line of code to add, and that's where we're going to save this 2-dimensional lattice to file. And then in our next code, we will convert that to a mesh. And then in the next computer session, we'll open up Blender and read that in, extrude it, play with it a bit, and we'll have converted this to a 3D lattice. Now sometimes when I have codes like this where they're taking a long time and I'm not sure whether it's stuck, whether I got an error or something like that, I will display a status, but I'll only do that the first time. Once I know everything's working and running, I don't need to worry about it. I can minimize this window and look for an error. Okay, no errors. It just is taking that long. It turned black because MATLAB doesn't like to refresh while it's working hard. I apologize for the delay here. I definitely got over ambitious. But we'll have a great looking lattice. Well, I'll tell you what, how about I pause the video until this finishes? That way you don't have to sit through it. Okay, we have our lattice. There's our binary lattice. I think that's pretty good looking. So let's close that. Let's save it to file so we don't have to rerun it. Save binary lattice to file. We'll save this to a mat file. We'll call it SV lattice 2D. We're saving SVLB. That's the 2-dimensional array containing only zeros and ones, whether there's material or not material. And we need to save the resolution parameters. That's dx2 and dy2. Now, rather than have to rerun the whole thing, we can select those lines of code. Well, the comment doesn't do anything. We'll select that line of code and just hit F9. And now it's saved to file. So that is it for this computer session. Thank you.